Welcome to this Central Region Convective Warning Improvement Project presentation on tornadic debris signature identification, a behavior-based approach. My name is Kevin Scow, and I'll guide you through looking at a TDS through a different lens and hopefully looking at a more inclusive way to define a TDS. So before we delve in, we want to ask ourselves, what is at the heart of identifying a TDS? And historically, we have been looking for areas of high reflectivity for a reliable signal, a velocity couplet for honing in on a tornado's location, and reduced correlation coefficient, indicating the debris being lofted by the tornado. And when the TDS was first identified, the meteorological community worked to establish thresholds for determining whether a signal was a TDS. However, there has been really no agreement on what these thresholds should be. Even more recent studies, since TDSs were defined in the early 2000s, have indicated that there is room for improvement, and Vandenbroek in 2015 really summarized this dilemma nicely, saying that specific thresholds of the polarimetric variables have proven challenging to define. Now, one thing to note is that TDS studies have noted the need for a couplet to be present to classify a signal as a TDS, but they're nebulous on what actually constitutes a couplet. And let's hang on to that thought. We'll get to that in a few slides. Since the TDSs were first defined again in the early 2000s, we've gained a number of temporal upgrades to the WSR 88D, including AVSET, sales, mesosales, and MERLs. So we now have a much higher temporal resolution data set to analyze, and so we can see the trends in the signals much clearer. So standing back for a few seconds, and let's think about what we are really sampling when it comes to a TDS. In this case, we have our hypothetical tornado right at the moment of tornado genesis in the center of the screen that is very well sampled by an 88D. And at this very moment, no TDS is visible by the radar. And initially, the tornado debris rises very quickly within the tornado vortex, and it appears in a very concentrated semicircular CC minimum on the lowest radar tilts. Over time, owing to centrifuging and storm relative flow through the storm, this debris cloud begins to widen and spread downwind. And this widening may not be as easily visible on the 88D owing to storm mode, beam height, product resolution, etc. So it's really recommended to put emphasis on temporal trends in the lowest tilt when it comes to ascertaining the behavior of a tornadic debris signature. And finally, once the tornado dissipates, the cloud becomes more diffuse and it descends and eventually fades away. And anyone who's observed smoke plumes or viewed output from high split runs, this should look really familiar. This behaves like any smoke or chemical plume, and the visibility of the plume will depend on the ambient hydrometeors present in the surrounding environment. We'll show some examples of that here in a few slides. So, remember when I mentioned to remember how all studies needed a couplet to call a signature a TDS? The fact of the matter is we rarely sample a tornadic scale circulation with the WSR 88D, just simply owing to its beam width and the location of the radar network across the US. If we see a circulation, is more often that we are sampling a mesocyclone or a mesovortex if present. Now, latest tornado research over the last 5 to 10 years has uncovered an increasing body of evidence that tornado genesis is a bottom-up process with near-surface vortex undergoing rapid stretching and amplification via an updraft, a mesocyclone, or a mesovortex. And some of these circulations can be quite shallow based on the storm mode or the environment. Meanwhile, TDSs are really a whole different beast when it comes to comparing them to tornado circulations. They contain light particulate matter and can quickly and easily be advected throughout a convective cell and grow larger and last longer than the actual tornado. So, putting that all together, this is a really key point, is that it may be possible to sample a TDS within a region of favorable tornado genesis without the presence of a radar resolvable couplet for some or even all of a tornado's lifespan. And this is particularly applicable for, say, land spouts, QLCSs, or even LP supercell modes. So with this in mind, let's go beyond product-based thresholds and actually look for the plume. First, let's start with the plume shape, a semicircular CC depression relative to its surrounding signal. And the difference between this depression and the ambient signal could be as small as 0.03 to 0.05, depending on the homogeneity of the surrounding CC signal. In cases of low precipitation environments, one may be able to use the behavioral characteristics of a reflectivity max to find a TDS. This process is scalable to both the smallest and the largest TDSs, with some TDSs as small as 4 contiguous super resolution CC pixels having been successfully identified with this technique. Next, we look for these plumes within regions of favored tornadogenesis, and this, of course, includes couplets, but also convergence zones. And for added confidence, maybe look for spectrum width maxima in the location of this plume to denote a potential circulation when velocity doesn't show anything. So really emphasizing that knowing your storm structure, knowing your environment to hone in on where those tornadoes may develop. Finally, assess trends in the plume. Ensure it is originating at the lowest tilt in a concentrated form and spreading upward and outward with height and time. Now, this last component requires a temporal continuity in the signature, and in a warning environment, time is of the essence. So I would say if you have high confidence in there being a TDS and the first 2 criteria are being met, take the appropriate steps as needed. Reserve this third step for times when you are less certain that a signature is a TDS. And in low precipitation scenarios, this may be difficult, and we'll show an example of this. Now, there has been no talk of product-based thresholds up to this point. The only real threshold maybe worth leveraging is a reflectivity threshold to help ensure you have adequate signal quality, say maybe around 20 to 25 dBz. But even then, there may be rare times when a TDS shows up in these lower reflectivity regions, such as with an LP supercell or a land spout. Each case will be different, and you, again, just need to understand your environment and storm mode and tune yourself in to help locate these TDSs. So let's put this all together, and the rest of the talk will focus on utilizing this technique across various storm modes. We'll start here with an HP supercell example. So here we're looking at the rear flank downdraft of the HP cutting across and moving towards the front of the storm. We have a broad circulation in the upper right, some decrease of correlation coefficient there in the circle, but it might be inflow contamination. So let's move on to the next scan and see what we have there. In a couple minutes later, this is a sales cut. You'll notice the reflectivity has spiked, the couplet has tightened, the correlation coefficient has dropped. So we're meeting both the shape and location components of this identification technique. Can't quite establish a trend yet because this is, again, a sales cut. But if we were to move one more scan into the future, again, a few minutes later, we'll notice that the correlation coefficient signal has widened and actually might be weakening based on the decrease in VROD and spectrum width. So this checks off the third component of our identification list. This example underscores how crucial it is to have some sort of mesosales or MERL scanning strategy active during a tornado. But let's be honest. Product-based thresholds that we have established beforehand to classify TDSs would have worked here. We had a couplet present. The signature was well within the realms of the current criteria that we use. So this was an easy case. Let's go on to something a little more difficult. So this case will go to a supercell with an elongated appendage. In this case, you can see the appendage extends back to the southwest from the storm, or beam heights roughly about 3,200 feet. So we have decent sampling of this supercell. Looking back at the tip of that appendage, where you might expect there to be a potential tornado, we do see broad cyclonic convergence, but no TDS really noted yet at this time. For reference, here is both the half degree and the 1.3 degree reflectivity and correlation coefficient cuts. just to show that really nothing out of the ordinary in this appendage at this time. Moving forward a couple of minutes, we suddenly notice an increase in reflectivity plus a drop off in the correlation coefficient right at the tip of that appendage. That should be getting our attention right away. And in all technicality, we're meeting the shape and location components of this behavioral-based TDS identification technique. But really, are we confident that a tornado is in progress? I don't know if I would be at this point. So let's step forward a couple of minutes, and we still see it is there at ½ degree. You'll notice that really sudden fall off in correlation coefficient there on the bottom left within that appendage. And the reflectivity is not all that high, so are we still confident that's actually a tornado there? However, if we go up and look at both the ½ degree and the 1.3 degree tilts, we see that fall off in correlation coefficient is extending vertically through the storm, well above 7,000 feet, within a signal of 20 to 30 dBz of reflectivity. So we're within the realm of calling this signal reliable, and so the drop off in CC is legit. Moving forward 10 minutes, you'll see that the appendage has gotten a little more diffuse, but there's still that really tight reflectivity ball. Not very high reflectivity, maybe 20, 30 dBz, but very steady state reflectivity sitting back there. That's been going on now for about 15 minutes, and a couplet really doesn't exist. I mean, you can see a spurious pixel of inbounds there, but for all matters, there isn't a couplet present, and there wasn't for the remainder of this event. And if you haven't noticed, the blue line on the background of this image is actually the tornado track. So we're halfway through the tornado at this point. And so without a couplet, this event fails the other methodologies for needing a couplet present for calling a signature a TDS. And a cross-section of that TDS really revealed how detached it was from the parent storm. And this image on the right is a great shot showing how the rear flank downdraft cut around the entire tornado circulation. This is, again, looking from the south. So you see the RFD has cut all the way around to the north side of the tornado, and there's really no precipitation anywhere near it. And given the shallowness of that circulation that you can see there, it's really no surprise that the radar was not resolving a couplet even at 3,000 feet above ground. The next example is going to be somewhat similar. It's going to be an LP supercell, kind of a landspout hybrid case, where in this example, there's actually two supercells present in this image. The southern supercell is just starting to put down a resolvable downdraft located within the region of inflow on the northern cell. The appendage that is the southern cell is more discernible at higher tilts, and I outlined it in black there so you can see it. It's very tough to discern at ½ degree, but looking aloft through the storm, given how close we are to the radar, it would show that the appendage extending back to this location. There's also a pre-existing boundary in this region. It's tough to see on radar, but if you were to step back about 15-20 minutes, you could see it's roughly tied to the tip of that appendage of the developing supercell. Next scan, suddenly you see a quick uptick in reflectivity values and a small concentrated ball with reflectivity values over 50 dBz in an area of very low correlation coefficient. First question I probably would ask, is this legit or is this an area of bad data? So even though we're checking off the first two boxes, let's go on and see if this signal continues. Sure enough, the signal moves a little bit, maintains that steady state ball-shaped appearance, and is starting to spread out just a little bit. So the trend aspect can be ticked off, and this is a legitimate TDS, despite the fact there's no sign of a couplet whatsoever at 700 feet above radar level. And if you were to gone up in the storm, you wouldn't really see anything. The mesocyclone was displaced well to the east and southeast of this circulation. And it keeps on going for another 5 minutes or so. No couplet ever showed up. And this scenario just, again, flat out failed the requirement for a lot of the product-based thresholds for needing a radar resolvable couplet. And this storm actually, a few minutes later, put out another TDS of very similar characteristics. And both tornadoes were actually photographed by the Iowa Department of Transportation web camera, shown on the left side there at the same time. And I did a cross-section of the radar reflectivity, again, showing how displaced that TDS was from the parent storm. And this is a great example of using reflectivity and velocity to diagnose the storm structure, kinematic fields, and even the presence of the TDS. And the dual pole data was just means of a secondary confirmation. Moving on to a QLCS example, this is one of my favorite examples from a TDS. There are two distinct boundaries that you'll note on the storm relative velocity on the upper right. The leading boundary there, arcing from the southeast to the northwest, is the leading updraft downdraft convergence zone, and this is moving to the northeast. And then there's a secondary surge right behind that boundary that's moving to the east-southeast. And these boundaries converge at the upper part of the image. First drop-off in correlation coefficient is just beginning to manifest itself in the middle of the left screen, located on the leading edge of that trailing surge just south of the triple point. There's an enhancement in the velocity values in this region, but it is really difficult, if not impossible, to tease out a true couplet there. As we go on to the next scan, that plume expands in area, meeting all three of our criteria that we have, even though, again, really no couplet present whatsoever. This next scan becomes really quite a mess. The original TDS is still present, although expanding and possibly fading, but there are now two more correlation coefficient depressions denoted in the yellow and pink circles, just a mile or two to its northeast, and again located on the leading edge of that updraft downdraft convergence zone, or right at the triple point there, so all within a very close proximity to one another. The next scan, the original TDS dissipates, but the two new TDSs are expanding, definitely meeting the trend threshold, so we have high confidence there's a tornado here. And this image is probably the best. You could say there was probably some sort of a couplet there, but it's hard to make out there on the leading edge of the updraft downdraft convergence zone, right on that triple point. And even then, it's kind of divergent in its nature there. The TDSs then merge at the end and then dissipate. And this is a great example of there being enhancements in the velocity data to hone you in on something might be happening there. But true couplets were hard to come by, and oftentimes we just couldn't tease them out from the background data along the edge of the updraft downdraft convergence zone. So instead of focusing for couplets, we look for favored regions on the storm using the three ingredients methodology to allow one to quickly hone in on the favored tornadogenesis locales. And just for verification's sake, the tracks of these tornadoes stood out excellent in cornfields. The left image is of the first TDS, and the right one is of those twin TDSs, twin tornadoes, which actually came together and merged into a single entity right at the end and then dissipated based on the aerial data acquired after the event. Now, we haven't gone into this much, and this won't happen very often, but there will be times that the correlation coefficient doesn't drop very much with a TDS, especially with smaller TDSs. As I mentioned, this is a bit of a scalable method, so this is a really tiny TDS that we sampled only at about 1,800 feet above radar level. It was at night, and there really wasn't much ground clutter along the leading edge of the updraft downdraft convergence zone, so the TDS was actually only 6 super res pixels in size, so not even a quarter of a square mile in size. And there really wasn't much of a spectrum with bullseye or a couplet. You could probably tease out, again, some enhancements in the velocity data, but it was really tough to hone in on a particular spot in the storm where a tornado was going to happen. And the average correlation coefficient here was greater than 0.8, which is too high for most TDS methodologies. And yes, it was a tiny tornado. The tornado damaged some trees and some farm buildings. There was really strong inflow on the south side that caused the majority of the damage, but the vortex itself, based on these satellite pictures, was only probably about 5 meters wide. So wrapping things up, first of all, what to look out for: the shape of the signal in the correlation coefficient, semicircular region of reduced correlation coefficient or higher reflectivity. Look at the location of where this signal is at. Does it make sense for tornadogenesis to be happening here? And then analyze trends if you're unsure of the signal. Is the signal behaving like a plume? Also, make sure that you have a appropriate scanning strategy in place before tornadoes happen, a higher sales count, or activating MERL if storms are close to the radar. Finally, have dedicated TDS procedures in place that can assess these trends in both the vertical and horizontal. Make sure you're using the raw correlation coefficient within AWIPS and not the smooth CC product. And if you're dealing with a rapidly evolving weather event in which many tornadoes are possible, maybe dedicate a person just to watch for TDSs and follow up with the warning METs to maintain situational awareness. And all of this is not to say that product-based thresholds are wrong. This is just an evolutionary way of looking at tornadic debris signatures that takes us to the next level to find those outliers and better improve our warning operations. Thank you for joining this presentation, and hopefully this helps you out in identifying tornadic debris signatures in the future.